All right, so let's talk about hashing today. I did a Google image search for the word hash, which you should not do at work, and this was the most wholesome image that came up, so this is it. So I want to talk about all things about hashing and Hashable and all that good stuff. So let's get right to an example. Let's say I have a struct, and it's got some properties, I'm sure, and some methods. We don't really care about that. That's not important right now. And so we have a struct, it's got some properties, and we want it to be hashable. So I'm going to make an extension on my struct. We need it to conform to hashable. And then if we look at the requirements for what hashable is, it needs a single property, read-only, as an integer called hash value. So that's the requirements of the protocol as of Swift 4.1. And we want to write our implementation, and we'll do something like this. So that is like valid code. This will certainly compile because we are returning the name matches. It's an integer, and 0 is indeed an integer. So this will all compile. But then the question is this correct? So we haven't talked about what hashes and hash values are, but maybe you are a hashing expert already, you work on the standard library or something like that, or you have some general intuition about what these things are used for. And so if I have an implementation like this and I return 0 all the time, then is this a correct implementation? So let's take a poll. Who says yes, this is, for whatever hashes are used for, this is a correct implementation? A couple of people, okay. And everybody else says no, this is not a correct implementation, you're doing it wrong. Most people, all right. So we'll come back to that at the end. Some people will be like, yes, I told you so. And then everyone else will be like, mind blown emoji. So what do we want to talk about today? Let's talk about what even is a hash. We'll go over that. We can talk about what are hash values used for. We'll look at that a little bit, but I'm not so concerned about what they're used for, but we might need to know that to understand how to do them properly. And then finally, how do I calculate good hash values if you do want to do it yourself? So it's the whiteboard coding part of the talk. There's no whiteboard here, unfortunately, but there was going to be a quiz afterwards. So let's talk about everybody's favorite thing, linear search or array search. So I have an array of stuff, numbers in this case, and I want to say, is some number in the array or not? So this looks like it could be a sorted array, but we'll just ignore that. It's just general purpose. So we want to search through it. So the way we'd have to do it is start at the beginning and go through the whole thing, and then worst case we reach the end and it's not there, or it's the last element and we'll get a yes or no. But this is not so great because it will become slow. If I have 1 million integers, it'll take some time. If I have 2 million integers, it'll take twice as long to search through, and so on and so on. So how can we make this faster? And if you're a data structure nerd, you'll say you should use a set, in which case you are hired. And sets can magically, for some reason, if you put 1 million integers into a set and you say, is the number 42 in there, it'll say yes or no, like, pretty quickly. And if you have 2 million integers, it'll still say yes or no pretty quickly. So like, what kind of magic is it doing? So we can kind of puzzle through this and say, how is it able to search more quickly? So we can say, well, we'll keep our array here, and what if we split the array? And we said, all the odd numbers go over here, all the even numbers go over here, or in this case, we say numbers greater than 5 go over here, less than or equal to 5 go over there. And now, if we say, is the number 4 in the collection? We can say, well, very quickly, we can say 4 is less than or equal to 5, it must be over there, and now we only have to search through half of it. Or if you say, is the number 100 there? We can say that's greater than 5, it must be over there, and then we can search much faster than we could before. And so if we kept doing this and we split it up and we split it up, and we're just basically putting the data into buckets, and we can say, gets a piece of data, decide what bucket to put into, and then put it there. And then when we search and we say, hey, is this value in the collection or not, we can very quickly say what bucket it's in, look in the bucket, and ideally there'll be like 0, 1, or 2 things in the bucket, and we can very quickly say yes or no. So that's basically how sets work. How it decides to do the buckets, how many buckets, like that's sort of beyond the scope of what we want to talk about today, but we want to do that. And you can imagine how to do it with integers. Again, we could do ranges, like 1 to 100 goes over here, 101 to 200 go over here, and so on. So we can imagine how to do that. But if you have some arbitrary piece of data, like a string or a puppy, and you're thinking, how am I supposed to know what bucket to put this thing into? And you say, if only I had a way to map an arbitrary piece of data into an integer, and then I could, based on that integer, decide what bucket to put it into. And you say, we have such a thing, right? It's our old friend, the hash value, which takes a piece of data, arbitrary data, and maps it to an integer, and then that's how a set can use it and put it into buckets and so on and so on. So this is sort of the magic piece of like what things might use a hash value. So I think this is the way to think about it. We get some data, and there's some kind of a hash function, and it turns it into an integer. So that's the basics of hashes. But there have to be some rules because, we're scientists here. We need some rules around this. So what are the rules? What are the invariants we need to maintain when we're talking about hashes and hash values? So the first one we'll talk about is equal values. I have two values, and they're equal. That means that their hash values must, underline, bold, non-negotiable, be equal. So this is really it. You can all take a picture of the slide. This is like all you need to know. If you have equal values, then the hashes must be equal. But I'll note that arrow only goes in one direction. So if I have some value, and I ask for the hash, and it says the hash, and then later on I ask for the hash again, I ask for the hash a million times, it should always return the same value, sort of, with an asterisk, which is the best kind of thing. So let's just look at the quick example here. So I've got a struct with a single field here. I'm going to instantiate it once, and then I'm going to print out the hash value twice, which is like, oh my God, is it going to give the same thing? We sure hope so. So I'll run this, and it will return the same hash. And I could copy and paste that code a million times, and it'll always be the same hash. So you might think, what I'm going to do? I'm going to get that hash file, I'm going to store it to disk, and I'm going to treat it like as a checksum. And then tomorrow I'm going to hash it again and make sure it's the same. But there's a note in the documentation saying not to do that, because hash values aren't stable between launches of your program. And you think, that's crazy. I launched the program a million times, and it's always the same. But that's sort of the documentation versus implementation. There's don't do this, please. Don't rely on this. But this is the kind of leads to subtle bugs, because it's you're relying on this behavior. So if I switch up here, no, I lost my mouse pointer. Here we go. Switch to the Swift beta, which I have up here. That's Swift 4.2, and I run this. Then you'll see I get some hash value, which is nice, -7513 ... I'll run it again, and they're still consistent, but you'll notice that it's different. So in Swift 4.2, there's a fix me in Swift 4.1. It's this should really be a random number, but it's a constant. So in Swift 4.2, they fixed it, and there is indeed a random seed. So at launch, the hashing mechanism gets seeded with a random value, and so they will be different across launches. But within the lifetime of your program, it'll stay consistent. So the lesson there is hash values must be consistent between launches, is sort of a little bit of an asterisk. So you shouldn't get your hash values and store them to disk and do other things like that, because that's not what they're for. All right. What else can we conclude? So we can say if the values are equal, the hash values must be equal. That's great. If the values are different, then that must mean that the hash values are different. Not enough people are shaking their heads, because this is not true. If the values are different, then it's totally possible for the hash values to be the same. And you're thinking, how is this possible? How can I live in a universe where non-equal values hash to the same thing? So to kind of puzzle that out, we'll have to return to this and understand that we're mapping a piece of arbitrary data to an integer. But if you think about how many pieces of arbitrary data are there, there's how many possible strings are there in the universe? I don't know, memory limitations, maybe if you ignore those. There's an infinite number of strings. And if you think about all of the types that you've created just in your application, how many instances of that type could you possibly make? It's an infinite amount of data out there. And integers are 64 bits, which is very big. There's 18 quintillion 64-bit integers. But compared to infinity, that's nothing. So we should have this intuition in our head that, yes, there is a lot of data out there in the universe, and there's no possible way that everybody could get their own integer. Although there are a lot of integers out there, there aren't enough. There aren't an infinite, well, there are an infinite number, but for 64 bits, there's only 64 bits worth. So with that in mind, we should think that hash collisions, two values hashing to the same thing, is totally normal, everyday occurrence. Although with an asterisk, it's not actually an everyday occurrence, but you have to think about it as if it could be. And so that's why this is something we should keep in our head too. If the values are not equal, then that does not necessarily mean that the hashes are also not equal. All right, what else? Correct or not correct? If we have two values and their hashes are equal, what does that tell us? Does that mean that the values are also equal? And then we would say, no, that's also not correct, because what we just said. Just because two values have the same hash, that tells you nothing about the values themselves. They could be equal or they could not be equal. So what we're left with is our original rule, the one big rule that you have to remember. Equal values means equal hashes. We can also sort of flip this around and take the inverse if you want to have two rules. And you can say, if the hashes are not equal, that must mean that the values cannot be equal, because if the values were equal, they'd have the same hash. Therefore, if the hashes are different, the values must be different. But rule 2 is really just a variation of rule 1, just to make more room on the slide. You really only have to remember, I would say, the first one, because that's the simpler one, I think. Equal values, equal hashes, and that's it. So we can go all the way back to the beginning, where our poor puppy has been waiting, with this implementation where we have a hash and we return 0. Everybody gets the same hash. So the question was, is this a correct, technically correct, the best kind of correct, some might say, technically correct. Is this a technically correct solution? And so the answer is yes, it is correct, because the only invariant we need to maintain is that equal values get equal hashes. And everybody gets the same hash here. So by definition, we've fulfilled the requirement that equal values get equal hashes. So this is a correct implementation, but it's not a great implementation. So my job application to the standard library team will still stand up. Why is this not good? It's because what we're effectively doing is we're returning 0 for everybody's hash. So when we have our set implementation, it's going to put everything into one bucket, which is fine, because the bucket can hold lots of stuff. But then when we ask the set, hey, does this thing exist or not, it's going to do linear search again, just like an array, and it's going to make everybody sad because the performance will be bad. So that's sort of the downside, I guess, to this very, very poor hash implementation, is that you could get slow performance, but it's technically correct. So that's the implementation again, technically correct. But I always like to know, well, what is a wrong implementation? Because that's kind of what I'm interested in. How can I totally screw this up? So this would be one way to do it, where you return a random number for the hash. So we can think this through and say, here's a value I'd like to store in the set. Of what's the hash? It's it's 57. Great, I put it in bucket 57. And then you give me the same value, say put this in the hash. And a property of sets is that they only store the value once. And so you say, here's the value again. And you say, what's the hash? It's oh, it's 85. You're oh, great, I'm going to put it over here in bucket 85. Now you have 2 of them. And then when I say, hey, here's this value, is it in this set, yes or no? It's what's the hash? It's oh, it's negative 105. And then you look in bucket negative 105, it's empty. And you say, no, it's not. And you totally mess it up. So this is an example of what not to do, maybe obviously, because then it will make people very angry. And then the puppies will get all mixed in together. And that's no good. So what's a way to do maybe I won't call it a better hash implementation. So if you're into cryptography, you know that cryptography is all just XORing numbers together, as they say. And so a classic way to do it is to XOR the hashes inside there. So our puppy struct had 2 properties, age and name. Age is an int, name is a string. Those are both hashable themselves. So I can take the hashes of the 2 components and XOR them together and get a hash. So this is one common way to do it. Maybe not great, but this is one way to do it. But it has some peculiarities maybe on its own. Should I advance? Yes, let's advance the slide. So let's say I have a puppy. It's going to be hashable. Let me just go back one and say that starting in Swift, I think 4.1, we got the automatic conformance. So if your properties in the struct are all hashable, you don't have to write this. The compiler will do it for you. So this is complete code. This will just work on its own. So I have a puppy. It has a name, and it has an age. And then I have another struct for a red panda, also has a name, but they're endangered animals, and so we keep track of them by sequence. We have all of them. We know about all of them. We keep them by sequence. And you'll notice, just by chance, the properties are the same. If you squint your eyes, there's a string, and then there's an int. So then the question is, if I instantiate a puppy with this name who is 8 years old, and I instantiate a red panda that happens to have the same name and is sequence number 8, and I take their hashes, then what's going to happen? So you can think about that. And let's give it a try. I lost the mouse pointer again. Do a little trick. Here we go. This is the code. Puppy, red panda, instantiate them, print out the hash values. I will go ahead and run this. And they're the same. So that gives us a hint about how the implementation is working. It must just be maybe going in order and getting the 2 values and hashing them together somehow, maybe with an XOR, maybe with something else. It doesn't matter. But they are colliding. And you think, oh my God, they're colliding. But then you have to also remember that that's okay. Hash collisions are totally fine. That doesn't mean that they're equal. It just means they have the same integer representation. They'll be in the same bucket. But that's okay. Just as a second curious exercise, let's look at this. So I have a struct here that is a string and then a number. And I have another struct that's a number and then a string. And then if I instantiate one of them with the string and the number, and I instantiate the other one with the same values, but they're in the reverse order, then what will happen? So if you, again, remember your interview questions about bitwise operations, and XOR is think the word is associative. I don't know. Commutative? Associative, I think. That's the thing where 1 plus 2 is the same as 2 plus 1. So A XOR B is the same as B XOR A. So if this is a simple XOR, these will be the same because it's the same values. If it's not a simple XOR, then they should be different. So you can think about how would Swift do it? How would Chris Latner do it? And we can run this, and they are indeed different. So there's actually a little addition, there's a little bit shifting going on, and that's why they're different. All right. So they're the same, again, totally fine because they'll just be in the same bucket, which is fine. They'll still look it up and they'll still be unique properly because they're different types, so they won't be equals each other. So equality and hashing are two separate, I'll just say separate, two separate things. If this is a problem, though, you have a lot of, you have like dog and cat, and there are like a million, every dog in the planet. Like I'm sure there's a lot of duplication between pet names. I don't know if there's a machine learning data sample about names of pets in the world, but I'm sure there's a lot of overlap between dogs and cats, for example. And there are a lot of values that would have the same name and the same age, and you think they're all going to sort to the same bucket, and for my implementation, that's bad. I don't want that. So I could write my own custom implementation and say, well, I'm going to, in my hash, I'm going to mix together the name and the age and the name of the animal. And then that way, a dog and a cat with the same name and the same age would hash differently if it were important to you. But the compiler will do it for you unless it's like a big deal. You've done some performance measurement and your set lookups are horrible or something. I'd probably not worry about it. So new in Swift 4.2 is that it adds another level of abstraction on top of the idea of a hash combining function. So over here, I just use XOR. If you look at the implementation in like Swift 4.1, you'll see it's like bit shift and some additions and some XORs, of course, because you have to have those. So in Swift 4.2, there's this idea of a hasher, which is the second algorithm up here. And that abstracts the hashing algorithm, of which there are many in the world. And it says, I will worry about exactly how this works. You just do the work of like passing me the values. So all you have to do in this hash function is call hasher.combine, and you give it each important bit of data. So you pass in the age, you pass in the name, it'll mix those together and run the hashing algorithm and output the hash value for you. So this is like the new Swift 4.2 way to do things. So if the question is, how do I write a good hashing algorithm? I would say, as they like to say, the best code is the code that you don't write. And so the compiler will do it for you. So in like, I don't know, 99% of cases, I'll be bold here, you should probably just you don't have to worry about it. You can just use the default implementation. If for whatever reason you found like performance is bad, you have a lot of hash collisions for whatever reason, then you can use, hopefully, the new Swift 4.2 stuff with the nice hash combining functions. You still have to support Swift 4.1, you have to do the hash value, and then you have to go to Wikipedia and look up the SIP hash algorithm or something, and then figure that out yourself. So let's wrap up. What even is a hash? It's an integer, 64-bit integer value that sort of represents your piece of data. But then maybe I'll add a side note of like what isn't a hash. So again, the idea of hash values, hashing and equality, I would say sometimes you mix them up in your head. You say, oh, the hashes are the same. That must mean they're the same. Or you think, oh, a hash is like a checksum, or it's like a unique identifier. But I think that's like, that way leads danger. So hashing, equality, just separate them in your minds. And a hash is just a convenient integer representation of your data. What are hash values used for? We see them a lot in data structures. Probably you don't call hash value yourself a lot, I would guess. But if you use sets or use dictionaries, you've noticed that items in sets have to conform to any hashable. Dictionary keys have to be hashable for this reason, for fast lookups. And how do I calculate good hash values? So again, number one choice, don't do it. Let the compiler do it for you. Number two, use Swift 4.2, which has hash combining functions. You can define your own hash combining functions if you're like a super nerd, or use the hash value property and write it yourself like that. So those are those three. If you like everyone likes puppies. If you like reading and you want to sort of read what I've just said for the last 20 minutes or whatever, then I have a blog post that is not published, but I will, as soon as I'm done, I will push the button and publish it. And it's sort of the article version of what I just said, so you can read it here and review it on your own time, on your commute or something like that. If you're curious about how the automatic conformance works, where you have a struct that has hashable properties or an enumeration where all the associated values are hashable, and the compiler magically comes up with it for you, and you're curious about how that works, I also have an article about how that works for equatable, where if all of your types in your structs are equatable, you get the equals for free. So the way that works is very, very similar to how it works for Hashable. So if you're curious about how that works, you can go to the same very fine website and find the article on automatic conformance for equatable as well. And there's a closing brace, so that means that's the last slide, and that's all I've got. So thank you.